Hello everyone. In this lecture we're going to start discussing new components. The components that we have already discussed include sources, both of the type dependent and independent, and resistors. And what was important for us in order to be able to analyze circuits that contain those kind of components was to figure out what is the equation that relates the current and voltage of that component. For example, with the resistor, we established that the equation is simply the Ohm law, the linear equation that says the higher the voltage across the resistor is, the higher the current that is passing through the resistor. And that's actually how we define the linear resistance. Now, let's move on to the capacitor. And first of all, let's understand what a capacitor is. And then immediately after that, I'm going to define what the equation for the voltage and current capacitor is, and move on to quickly show you that including capacitors in any circuit would not change the algorithm that we use in order to analyze the circuit, and only basically what's affected is the math. The math component of it is going to be different. We're going to quickly see why that is, but other than that, the algorithm stands true, and that's all you need to know in order to do the analysis. So what's a capacitor? So the capacitor is basically two conductors that they are not electrically connected to each other, and rather they're brought close to each other. Now, bringing them close is not a necessity, meaning that even if you don't bring them close, there's still a capacitance formed as a result of these two capacitors. Like between any two conductors in the world, you can define a capacitance. Now, when you move them away from each other, the capacitance becomes so small that it is negligible, and most of the time, we don't even need to consider that there is such a capacitance between those two conductors. But generally speaking, between any two conductors in the world, you can define a capacitance. Now, when you bring them close to each other, then the capacitance value increases, and if you bring them close enough, the capacitance is so large that not only has to be counted, but also could be used to basically add functionality to a system or a circuit that uses that component. And we're going to see what kind of functionality would that be. Okay, the functionality that we discuss here is really coming from the fact that every charge creates an electrostatic field around it, and that electrostatic field affects other charges. So an electron, being an electrical charge, creates an electric field. That electron therefore affects any other electron or any other charge that exists. Now, you bring two electrons really close to each other, the effect becomes really large. You basically have a negative charge, and these two start repelling each other, and the force becomes stronger and stronger as you bring them closer and closer to each other. In the capacitor, what happens is that since inside the conductor and there are charges and they can move, once you connect the two sides of these two conductors to a voltage difference, the voltage difference causes an electric field large enough of an electric field to be established between the two conductors, so that these charges actually can move each other, like the field or the force that is felt from one conductor can be strongly felt on the other conductor, so the charges start repelling or basically attracting each other. So once you apply a voltage between the two, you start getting charges accumulated in here, meaning that if I say take a battery and connect that to this. Let's say this is positive and negative, meaning the voltage on this side is higher than the voltage on the other side. Then you start establishing an electric field here, and charge would build up on the capacitor. what that means is that you're going to start getting electrons here. The electrons repel the electrons on the other side, so you get current going in this way. This is current, or you get, in other words, electrons going in the other direction and start filling up the two conductors that are really close, the surface of the conductors that are really close to each other. So what's the use of this? If you notice, once you establish this electric field, you can basically use the capacitor as a way of conserving potential energy, basically. So you have these charges that are here, and they contain some potential energy, and that potential energy is conserved as long as that charge stays there. In all the kind of different work that you do in the world, you always move, we kind of discussed this very early on in the introduction, you transform energy from one form to the other, and one of the two forms of energy that we always work with is potential and kinetic energy. Passage of current in electrical domain is associated with kinetic energy, and the accumulation of charge is associated with potential energy, and transformation between the potential to kinetic, or from charge to current passing through the circuit, has a lot of applications, and we're going to see that later on. Accumulation or conservation of energy in potential form, obviously one of the easy ways of understanding how useful that is that if once you conserve that, you can keep it as long as you need and wait for the time that is required, that energy is required, and then release that energy back. Some kind, like something like a battery, you can think of it. So obviously conservation of energy in that form could be useful. Okay, so how do you define the capacitance for this new component that we just basically invented? It was simple. Two conductors brought really close to each other. Okay, now the capacitance is defined, the symbol that you use is C, and the way that you define it is that you're saying that when I apply a voltage equal to the V and connect it to the capacitor, there's going to be charge accumulated. You're going to measure that charge, call it Q, divided by the voltage that was applied to the component, and what you get is a value that you, from now on, we're going to call it capacitance. That's the capacitance associated with that component. And this is a constant number for the most part. You can assume that it's accurate enough to assume that it's a constant number. In other words, this equation is linear with respect to charge and the voltage. Now, if you double the voltage that is applied to the same device, you get double the charge. Okay, so now how does that capacitance relate to the physical properties of these two conductors? That's something that we have seen at least partially in physics. One of the simplest ways of making these capacitors is to bring two conductors in the form of basically planes really close to each other and keep them at a constant distance. And there are simple calculations that you can calculate the capacitance associated with these two planes brought close to each other. You can calculate the capacitance associated with two conductors in any shape, at any distance, or at any variable distance. But that's really not the discussion for this specific circuit analysis lecture. All we needed to establish is this equation where it shows us that between the charge and the charge accumulated on the two conductors and the voltage applied across the two conductors, there's a linear relationship, and the constant as a result of dividing the charge by the voltage, we're going to call it capacitance from now on. Now, notice that this equation is still not giving me what usually I'm interested in when I'm doing circuit analysis, which is voltage and current. But we know that current is basically derivative of charge with respect to time. Now, since it's the derivative of charge with respect to time, this current is actually a function of time, right? Assuming that the charge is a function of time, taking the derivative of charge with respect to time becomes a value that is a function of time. Now, going back to this, if I'm looking for an equation that gives me the functionality of this component in terms of the voltage that is applied across it and the current that is passing through it, I'm going to rewrite that and show you that Q is equal to CV. Now, if I take the derivative of both sides, dQ dt is equal to C dVT dt. Now, dQ dt is IT, the current, and that's C dVT dt. And this is the equation that I was looking for, that relates the current and voltage of a capacitor. Okay, so immediately you realize that this equation is no longer a linear equation. It's no longer similar to what we saw in resistors, where there was no dependency on time. With the resistors and the sources and the circuits, simple circuits that so far we have analyzed, we never saw any dependency on time. In other words, the values for the voltages and currents in our circuits really didn't change over time. So we never considered time as one of the variables in our circuit analysis. But immediately with this equation that we have with a capacitor, you realize that the current and the voltage of a capacitor are a function of time. And because of that, the kind of math that we're going to end up doing from now on, once you include a capacitor in your circuit, would be different than what we have been doing so far. Okay, so before we move any further and discuss other properties with capacitors, let's do something really quick. Use this and then do a simple circuit analysis using a capacitor and see to establish that all we really needed to know is this in order to do circuit analysis. Say I have a source that is connected to a resistor and a capacitor. Very simple circuit. Now, from this point on, everything is a function of time. All the voltages and currents are function of time. So this source has a voltage, but this voltage is not constant. It's actually changing with time. Now, when I want to analyze this circuit, I'll go through the same three-step process. Label the circuit. This would be my ground. This is my VST equation for that component. And I'm going to call that VC. Okay. Now, to be careful, I'm going to rewrite this equation in a form that we're going to use from now on, and always stick to that. So let me take this away, which was part of our definition. Redraw the capacitor. Say this is V1T, this is V2T, the voltage on the two sides. This is IT, the current passing to the capacitor, and the equation for the capacitor equation is IT is equal to CD V1T minus V2T over, actually, so dV1T minus dV2T, dV1T minus V2T over dt. This is the same thing. The only difference is that I am pointing out that this voltage that I was putting here was a differential definition, meaning that you take the voltage on one end of the component, subtract it from the voltage on the other component, take the derivative with respect to time. And that's sometimes get neglected, and there are reasons to be cautious about defining it exactly how the voltage is defined on any component, including capacitor, which is the voltage on one end minus the voltage on the other. Going back to here, now I'm done defining all the components in the circuit, nodes in the circuit. Now the current here, I'm going to call that IST. Now the same IST is going to pass through the resistor. Same current is going to pass through the capacitor. I'm going to keep on putting that T in there to always remind ourselves that these voltages and currents are now function of time. But other than that, everything else is the same. Before we would call that VS, VC, and IS. Now I'm calling that VST, VCT, and IST. There's no KCL to be written here. Equations for components, I already wrote the equation for that component. I need to write the equation for these two. So for this one, equations for components for the resistor and capacitor. So IST is equal to VST minus VCT divided by R. For the capacitor, I use that equation. IST, the current passing through the capacitor, is equal to the C, the capacitance value, D, the voltage on one side is VCT, the other side is 0, so that would be dVCT dt. Now, I have to solve these two equations to calculate all the currents and voltages in the circuit. So let's move on. These two are equal to each other, so I can put these two equal. That means VST minus VCT is equal to RC dVCT dt. In other words, RC dVCT dt plus VCT is equal to VST. Now, if VST is given, this equation only has one unknown. R and C are known, and VCT is the only thing that is unknown, right? So one equation, one unknown, and I should be able to calculate what VCT is. The only point to notice here is that this is not a simple equation, algebraic equation that we use to solve. This is actually a differential equation. So in order to find out what VCT is, I have to solve this first order differential equation. And there are ways to do that. As long as you know what VST is, you can actually calculate VCT. And that's part of the math that we are doing. So the math component of the calculation when it comes to analyzing circuit with capacitors would include solving differential equations. But really, the algorithm to do circuit analysis is no different. You do exactly the same. You get the differential equation, solve it, and as a result, you get all the currents and voltages. Now, obviously, this VCT becomes an equation that is a function of time, and that's what we expected. We said because the equation for that relates the voltage and current of a capacitor is a function of time. Everything in the circuit, all the voltages and currents are going to eventually become a voltage, a function of time, and that includes VC. Now, as soon as you calculate VCT, then you can put it back to, say, this equation, take the derivative of it with respect to time, multiplied by C, that gives you the current that is again a function of time, and at which point you have all the voltages and currents in the circuit. So the algorithm stands the same. It gives you the technique or methodology that need to follow in order to calculate all the voltages and currents in a circuit once it includes the capacitor, but the math is going to be different. Now, I'm going to stop at this point, and we're going to move on to do more with capacitors before we kind of quickly open a parentheses, show you how to calculate or solve first order differential equations, and then come back and finish the math associated with the analysis of components, including capacitors. Thank you for your attention.